sorry, had a little break there for you to ask questions and think about it. So I was just pointing out that we have this concept of information loss of a measure preserving map, which is just change in entropy from the initial random variable, initial probability measure space, the name for the same thing, to the final one. But that is just sort of set up so that it very obviously gets along with composing maps. So the total change is the sum of the change over the two steps. So we get that this information loss converts composition of measure preserving maps into addition. Now, if you're a category theorist, you'll immediately think, aha, that's a functor. A functor is something that preserves composition. So here, information loss of a composite is some kind of composite of information losses. However, you'll notice that composition here is going under the name of plus. So if you're a category theorist, you'll immediately think, okay, there must be some category lurking around here where composition goes under the name of addition. And indeed, there is a famous category of that sort. Namely, there's a category with just one object and the numbers from 0 to infinity as the morphisms from that object to itself, where composing two of those morphisms is just addition. So you may think of this as a devious trick to turn a perfectly simple thing into a category, and in some sense it is, but it's not really devious. It's just whenever you have any sort of associative operation, it's probably composition of morphisms in some category. And so this is the category which I will call 0 to infinity. So here it is. There's a category that has just one object. Don't ask what it is, so I'll just call it star. But the meat is the morphisms from that object to itself, which will be the non-negative real numbers, and addition is composition. And so what we're getting is that information loss is a functor from finite probability measure spaces to this category. So when we're saying that, that's a way of saying that this is a way of summarizing information about finite probability measure spaces and about the measure preserving maps between them in some simpler category. This simpler category has just one object, so all the different objects here are just getting sent to that one object. So in some sense, we're completely throwing out everything about the objects by means of this functor. But the meat, as I say, is in the morphisms. There are many different morphisms in here, which will have different amounts of information loss. And here we're summarizing how much information loss we have by means of a convenient category, the non-negative numbers. That's a good category for measuring amounts of stuff. So the question is, okay, great, so you've managed to make it sound complicated and say it's a functor, but where it gets interesting is, can you characterize this functor? Can you use this language to say that this information loss functor is the only functor, or maybe the only functor that has a couple of properties? And it is. It's convex linear, which I'll explain, and it's continuous, and up to a scale factor, up to a rescaling, it's the only functor with those properties. So this is giving us a way to say what's so great about entropy. So let me talk about convex linearity and then continuity. So there's a way to take convex linear combinations of finite probability measure spaces. Convex linear combination is a linear combination with you're taking, for example, a combination of two things, and the coefficients are numbers between 0 and 1 that add up to 1. A special type of linear combination. But here, we're doing something a little fancy. We're taking a convex linear combination of two finite probability measure spaces, which I'm now writing this way. So it's a finite set and a probability measure on it. And so how do we do that? Well, I need to get a new finite set with a probability measure on it. And so for the finite set, I'll just take the disjoint union of those two sets, x and y, and then I need to put a probability measure on it, and I'll just take c times the probability measure that's on x, and 1 minus c times the probability measure that's on y. That will, again, be a probability measure because we know that all these numbers in P add up to 1, and all these numbers in Q add up to 1. So if we multiply them by these numbers, then the collection of all of them will add up to 1. So the idea here is that we think of a finite probability measure space as a set of possible things that can happen with different probabilities for them happening. And if I have two of those, I can combine them into a bigger one by means of flipping a coin that has probability C of landing heads up. So I could either have some random selection of sandwiches I could serve you, or some random selection of different kinds of pasta that I could serve you. But if I want to combine those choices, I could first flip a coin that's a 2/3 probability I give you a sandwich, which I select according to the probability measure P. Remaining probability, I select an order of pasta. So it's just the most very sensible way to combine probability measure spaces into bigger ones. And you can also define convex linear combinations of morphisms. So if I have a probability preserving map and another one, I can get a new one, which I'll call the convex linear combination of those two. And this is the most long and disgusting formula in the whole talk, but it's almost contentless because it's just going from the obvious convex linear combination to the obvious one. And the definition of it is completely pathetically obvious. This is just a function from this disjoint union of x and y to the disjoint union of x prime and y prime. And what is it? Well, it's just a function that's equal to f on x and g on y. So that's just the only way you could define things for morphisms. In category theory, whenever you do something for objects, you want to do it for morphisms as well, to make you be a functor, fundamentally. And so the point of this is that information loss has a very interesting property. It's convex linear. So here what I'm doing is I'm flipping a C-weighted coin, a coin that has probability C of landing heads up. And I flip that coin, and then using the result, I either apply some deterministic process F to some data, or some deterministic process G to some other data. How much information is lost? Well, it turns out that it's exactly the simplest thing you might hope for. It's kind of a linearity law holds. Checking that is not so obvious. The reason is that the entropy of one of these mixtures of probability measure spaces, convex linear combination of measure spaces, turns out to be given by a fairly simple formula, which is you take the entropy of the first one, multiply it by C, the entropy of the second one, multiply it by 1 minus C. But that's not all. There's a little more entropy in there due to the random choice involved in this coin flip. And that is really just the entropy of the coin. And so this is the formula for how entropy works when you do convex linear combinations of objects. But then information loss is a change in entropy. And so when you calculate information loss, you do a formula like this minus another one. And so this coin flip thing cancels out, and we're left with just a linear law. So it's simpler, actually, to think about the information loss of a process rather than the information in a probability measure space. It is a simpler law. So it's convex linear, and information loss is also continuous. So I don't want to rake you over the coals of this in too much detail, but there's a way to make these things, fin prob and zero infinity, which are categories, make them into topological categories. A topological category is just a category that has a topological space of objects and a topological space of morphisms, where everything, all the maps involved in the definition of a category, meaning composition, are continuous. So, all of that's a fancy way of saying that we all know what it means to change a number from 0 to infinity a little bit. You can also guess what it means to change a finite probability measure space a little bit. You have some set, a bunch of probabilities on it, you can change those probabilities a little bit. And so information loss is continuous. If you change something over here a little bit, the amount of information loss gets changed a little bit. The reason why we need this continuity, the reason why we need to talk about it, is that in the theorem that I'm about to state, it really wouldn't be true if we didn't impose this extra condition of continuity. So here's the theorem. So together with Tobias Fritz and Tom Leinster, I proved the theorem that any continuous convex linear functor from finite probability measure spaces to numbers from 0 to infinity is a multiple of the usual information loss. So in other words, there's some constant alpha such that if you give me any morphism over here, it gets mapped to alpha times the information loss, where this is defined using the formula for Shannon entropy. So that's a really nice theorem, in my immodest opinion, for the following reason, that the assumptions here, convex continuity, some kind of niceness assumption. Convex linearity is just a kind of linearity assumption. Being a functor, we saw, means that when you compose morphisms here, it goes over to the sum of numbers here. So those assumptions all have a kind of linear flavor to it. They only mention multiplication and addition, and are linear in character. But from these assumptions, we're getting that the information loss has to be given by this formula involving p log p, which is a sort of weird looking function. It's not at all linear looking. So it's not obvious, I think. So I won't give the proof, but I'll just say that there's an easy part of the proof, which is to show that any functor like this really has to be measuring some kind of change. That is, if you have some measure-preserving function g, the functor has to be of the form something about the probability measure space you started with minus something about the one you ended up with. So there's a quick little calculation you can do to check that. And then the hard part is to show that that something, which I'm calling phi, really is the thing we know and love. And you get that by repeatedly using the axioms over and over again, and then using continuity to show that this formula holds not just for a dense set of probabilities, but for all of them. So I won't really give the proof, but you can just click on that blue thing and you'll get the proof. So there's some generalizations of this, which I want to zip through, I guess. So, in fact, there are other ways to make this category into a category in which convex linear combinations are defined. So there's an abstract definition of a convex structure on a category. There's sort of the obvious one, where you take the obvious way of taking convex linear combinations of numbers, but there are other weird ones, and they're completely classified. They depend on a parameter. And so it turns out that if you use those and then demand that this functor be convex, linear, and continuous, you get other weird notions of entropy, which are in fact already known. So Sales studied a kind of entropy given by this other bizarre function here that depends on a parameter beta, which you can check using L'Hopital's rule. You can check that it reduces to the usual entropy in the limit as beta goes to 1. So this sort of explains that these other non-standard entropies really do fit into the framework. If only certain people are interested in these non-standard entropies, and so I don't expect that most of you care about that, but anyway, it's true. Something that's a little more, less of a specialist kind of interest here is that entropy is a special case of something called relative entropy. If you have two different probability distributions, P and Q, on a finite set, there's a concept of the information of P relative to Q. And that has the following meaning. It's how much information you expect on average to learn if you had previously thought that the correct probability distribution of the outcomes was Q, and then someone tells you, sorry, no, it's really P. You might do experiments and discover P. How much information do you learn when you change your mind in that way? So it's a generalization of ordinary entropy that in some sense is really more fundamental actually than ordinary entropy. It can be infinite, among other things. It can be infinite if you thought that something was impossible that had probability 0, and then someone says, no, it can happen. So then you're very, very astounded and you gain an infinite amount of information. So there's a category theoretic characterization of this thing too. So it uses just a somewhat fancier version of the category we looked at before. So here's a morphism in this fancier category. So we have a probability measure space, another one, a measure preserving map going forwards, just as before. But now we have this other thing, a stochastic map going back, which has the property that if you go back and then forwards, you get the identity. What's that thing going back? It's a hypothesis. It plays the role of a hypothesis. So what I mean by that is you should think of this as some kind of system you're measuring, and this as the measurement apparatus. And suppose the measurement process is completely deterministic. So any state of your system here gets deterministically sent to some reading of your measurement apparatus, like the position of a dial. But that you measure may not completely be enough to determine what the original system was doing, but you could make a guess about what it was doing. And that's what this S does. So for any measurement reading, you guess a probability distribution of states on the system. And this is a kind of consistency condition. It says that if you make that guess and then go forwards, you do indeed get back where you started. And so this is a category where you should think of the morphisms as being a measurement process together with a hypothesis about the system you're measuring. And that's a situation where you can talk about relative entropy, because in this situation here, there will be a probability measure on the system X. We could call that like the true probability distribution of states of X. And then there'll be another probability distribution on there, which is what you get by taking the probability distribution of states of your measurement apparatus after you've made the measurement, and then use your guess. So compose that stochastic map with that stochastic map to get another probability distribution on X, which is your guess about the probability distribution of the states on X. So there's the truth, and then there's your guess about the truth. And that's sort of the situation where relative entropy is important. You can then suppose someone tells you the actual truth, then you would learn something. So we could talk about how much information you'll gain if you learn the true probability distribution of states of the system, given your guess, your best guess. So sometimes your best guess is right. So sometimes when you take your probability distribution of states on Y and you compose with your hypothesis, you actually get the exact correct probability distribution on X. And in that case, it turns out that, as you might expect, this relative information is 0. So if your guess about something is right and someone tells you the truth, you don't learn anything because you already knew the truth. So that's good. So there is this category that I mentioned before, and then there's this category which for some stupid reason is called FP, which are the ones where your guess was right. Morphisms where your hypothesis is optimal. And we know relative entropy vanishes on that. And so then the theorem, after this long build-up, is very short. So, same kind of hypotheses. Any continuous convex linear functor, but now from this category where the morphisms are a measurement process together with a hypothesis, to this category here, which is like the one we saw before, but now we actually need to include infinity as a possible outcome. So any functor like that vanishes on the morphisms where your hypothesis was exactly right has to be a constant multiple of the relative entropy. This theorem is tons harder to prove than the first one, actually. I would have given up, but Tobias kept digging away and proved it. So if you're the sort of person who likes to outdo other people, please do that, okay? So click on this blue thing and find a better proof than we have of this. I feel there should be one, but it couldn't find it. But anyway, the statement is nice and simple. Okay, so I should stop pretty soon. I just want to say something about a somewhat different topic. So, Brendan Fong here has written a paper called Causal Theories, a categorical perspective on Bayesian networks. He's a show-off, so instead of using this category thin stock that I've been talking about finite sets and stochastic maps, he was actually mainly focusing on one where you don't require that the set to be finite. But let's not worry about that, because we don't have enough time to talk about that. I want to talk instead about what he did with it, which is different than I've been talking about so far. It's studying Bayesian networks. So, a Bayesian network starts out being a picture like this. So you have a bunch of different variables, how much it's raining, how much it's sun there is, so on. And these arrows, edges, which represent causal relationships. Something could cause something else. So what we've got here is a directed acyclic graph, a graph where the edges have directions and there are no cycles. And that's all we've got. That's a Bayesian network. But you intuitively think of each vertex as being some variable, and you think of each directed edge as a causal relationship. And the idea is you want to think about models of the world based on this Bayesian network. That is, so far, I have not associated a particular set to A, but you might want to. You might want to say, okay, it's either raining or not, so I maybe want to have a two-element set of those two possible conditions, raining or not, or maybe how much it's raining. Use a 100-element set. So we might like to take this model here and instantiate it in some actual sets and functions, or maybe stochastic maps. And so, roughly speaking, this is what Brendan does. Actually, this, he didn't say he did this, so I'm sort of reinterpreting what he did after reading it. Maybe it's true, maybe it's not quite true. I think it's true. So, I think what he did is start with this directed acyclic graph and forms a category out of it, which is a category that has finite products in the categorical sense. It has one object for each vertex, and one morphism from a product of those objects to some other object, whenever the AI are all the parents of B. That is, all the guys that have edges going to be, all the guys that have edges going to be. So for example, here, if I pick D, this could be like how happy you are in England. It seems to be mainly based on, what did I say, how much it's raining and then how sunny it is. So both of those affect you. Of course, whether it's raining affects how sunny it is. But we will put in we'll put in our category a morphism from A times B to D, representing the causal relationship of these two factors on your happiness. So we build a category with finite products out of those generators. And in particular, if there are no parents, if you have a node that has no edges going to it, that means a morphism from the product of no things. So that's called the terminal object, B. Notice that subtlety. And so that's what he calls the causal theory described by that graph. So it's a theory in the sense of, well, in the sense of Levier, who liked to think of theories as being categories. And then the point is that a model of that theory can be described as a functor, which basically is preserving, well, it's a symmetric monoidal functor, meaning preserving products, roughly speaking, which sends these abstract variables here to actual sets and sends the morphisms to stochastic maps. So there's some stochastic map from the weather conditions to your happiness. They don't determine your happiness, but they influence your happiness. So I'm starting to use jargon the way people do at the end of talks. They say, okay, I'm sick of trying to really explain things. I'm going to use more words that I didn't define. Okay, but if a lot of you know some category theories, I don't feel too bad about that. But then unpacking that slightly, what it means is that we get a finite set for each vertex, each variable, and then we get a stochastic, well, we get various things. As I said, if somebody has no parents, if a vertex has no parents, we get a stochastic map from the one element set to its set, and that's, as I said, just the same as a probability measure. And then more generally, if some node has a bunch of parents, we get a stochastic map from the product of those sets to it. I'm just unpacking the short thing on top. And in particular, from that we can get a random variable for every vertex, because we start out with random variables, i.e. probability measures on the sets of the vertices that are the guys with no parents, and then we can propagate them down, apply stochastic maps to them to get probability measures for all the other vertices. So the idea is that there'll be some things that are sort of determined only by the gods, how rainy it is, how snowy it is, and they will have implications for other things that are affected by them, and you get a probability measure ultimately on for every vertex there. So this is a very slick way of talking about things that people already have talked about in Bayesian network theory, but I think it's a less ad hoc kind of way. And in particular, just automatically from this abstract nonsense, these random variables will automatically obey the kind of independence assumptions that people want in their Bayesian networks. So in other words, if two vertices have no ancestors in common, their random variables will be independent. They'll be what's called stochastically independent. So the idea is that the only dependencies arise from common causes. So with that brief sketch, that ends my series of talks here. And so I've been trying to outline a big bunch of stuff that's just partially worked out. We've seen how category theory connects signal flow diagrams and electrical circuit diagrams, where we are using vector spaces and direct sum as the tensor product, linear maps, which we know. Stochastic Petri nets and chemical reaction networks, two formalisms for basically the same thing, used in subjects like chemistry, epidemiology, population biology, where it's basically looking at Feynman diagram-like structures, but where processes are probabilistic rather than quantum processes. And now today, following that kind of stochastic theme, looking at Bayesian networks and seeing how information and entropy, those allied concepts, arise naturally just from this category theoretic point of view. So I'm hoping that in the future these different branches of the topic I'm discussing will fit together better. I really enjoyed giving these talks, partially because I realized how incoherent these talks were. Well, hopefully each one individually was coherent, I hope, but what I mean is that they really, I think of them as all being part of a single subject, but I wasn't able to give a presentation that made it look like that exactly. We have a bunch of different categories running around here, many of them involving random processes, but they should be integrated. And the reason why they should be integrated is because all sorts of people are studying complex systems made of interacting parts, like chemistry, biology, all the things people model with Bayesian networks, the things electrical engineers do. They're all really trying to do very similar things, but they're so focused on what they're doing that they don't necessarily step back and look at the relationships between what they're doing. And category theory is exactly designed for that. Category theory is the branch of math that lets you take a bunch of things people are doing and see them as in a common framework, and then set up lines of communication between different things, different communities of people. And so, as I said, I'm trying to ultimately do some good here to our ecosystem, which is sort of the ultimate complex system made of interacting parts. Understand it, help it. This is not a request for money when I say please help. This is a, you click on this and you'll see all sorts of scientific projects that a bunch of people are doing in a project called the Azimuth Project, which on the mathematical side is focused on this network theory, and on the more practical side, we're trying to sift through the arguments that people are having about global warming and other ecological issues and try to get a get a wiki going of fairly reliable information about those subjects. So somehow that's all supposed to fit together someday. Okay, so thanks.
Questions?
Yep.
I have a very naive question, so I'm
Good.
hoping I just got tangled up in your metaphor.
Uh-huh.
Go back to the slide where you were looking at relative entropy and there was the word optimal on it.
Yeah. There.
Yeah, so can you show the whole slide?
Yeah.
Right, so given the way you set things up, I can understand why the answer is 0.
Uh-huh.
But on the other hand, it seems like you've learned something very important.
That you're right.
That you're right. And that you should stop.
That's some kind of, yeah, that's some kind of meta learning. So we don't have any thing in this formalism about knowing that you're right. When I write down this formula for relative entropy, which is sort of what's underlying this functor, this is the way I intuitively say it is that if you thought things were distributed according to Q and then someone tells you no, it's P, you've learned something, and this measures how much you've learned. And it's, when you're thinking about that, it's very convenient often to think of P as being the truth. Q is your opinion before you hear the truth. But there's nothing in the mathematics about that. There's nothing in the mathematics that says that P is true. Right? So P could be a lie. Right? So you could learn, quote, what you thought was the truth, and it's a complete bunch of baloney. You're fooled into believing it, and you would have gained a lot of information. But there's nothing about information theory that says the information is true. It's just, you know, obviously, you can read newspapers. There's a lot of untrue information, and information theory is not mainly about that. So when I say that P here is the true probability measure, that's a very useful way of thinking about this, but it doesn't really enter into any of the calculations. And if I were being a hardcore Bayesian, I would avoid ever saying the phrase the true probability distribution, because they regard that as like a sort of a contradiction in terms.
But I guess extending your metaphor then, if there's nothing left to learn, you can stop.
Right. So, I mean, this is, you learn, you can stop learning, right? That's right.
Okay, any more
Bob?
There seems to be a slight conceptual difference between what people understand usually as convex combinations
Uh-huh.
and these ones, because even if your sets are the same, you treat them as different. While
Right.
usually convex combination, you mean mixing together.
Right, that's right. Yeah, this is a funny thing where there's we've got a category, and if you give me any two objects in it, I can form this funny new object that's called a convex linear combination of them. And similarly for morphisms. And if you want to make it more detailed or fancier, there's a thing called an operad for convex linear combinations. It's just a thing that has convex linear combinations as its operations. There's a concept called a convex set, which is a set where you can take convex linear combinations of elements. So that's what you're very often seeing in foundations of quantum theory or probabilistic theories. But here what we're doing is we're letting that operad act on a category. So we can talk about convex linear combinations of objects and of morphisms in a functorial kind of way. And it's only for that way of thinking about things that you actually get this nice property that information loss is convex linear. Yeah. So it's a somewhat different angle on things.
More questions?
Yes?
Do you think the condition that your assumption that you're only working with finite sets is actually important, or just a technical simplicity?
It's going to be just a technical simplification. If you work with infinite sets, the main thing that you have to be careful about is that this can then become infinite, so it goes all the way up, including infinity. So you have to adjust the statement of the theorem, but it probably can be generalized to that. And if anyone likes analysis, that would be a great project to work on. And so it's basically that we wanted to avoid extra work. So I would presume the good way to deal with a general case is you take a probability measure space and you in some sense approximate it basically by chopping it up into chunks, a finite set of chunks, and get a finite probability measure space. And use the theorem for the finite case to boost your way up by approximations to the general case. And that's a pretty good idea in general, because that kind of thing would be a morphism in your category. So you'd start out with this probability measure space that may not be finite, and then this would be the set of chunks, and there'd be this map here, which would be a quotient map, which would be one of these morphisms in our category. So then you could use the functoriality to gain information about what's going on here from these approximations. But yeah, I've been thinking that if I ever get a grad student who likes analysis, I'll make them generalize both these theorems in the way that you're suggesting.
Okay, no more questions? Then let's thank John very much for this.
Thanks.